Hello guys, today I will talk to you about the Keto-Enol Tautomerism, and I will also talk to you about something called the Aldol reaction, and I will explain all the terms that I just used, and I will also show you guys a couple examples of how this works. So, first of all, keto. Keto just stands for the ketone, and I'm going to put in brackets or aldehyde, because this also works for an aldehyde as well. Right, that you have as your starting molecule. And we know that ketones look like this, and aldehydes look like this. So I will ignore the aldehyde for now, while I show you guys how to do the Keto-Enol tautomerism, and then I will show it with the aldehyde. So in order to do this thing, you're going to need a base and something like NaOH, which has a full negative charge on the oxygen. And some people your first reaction might have a nucleophilic attack on this partially positive carbon, but actually that would be wrong, because this OH, first of all, we know two things about it from general chemistry. We know that it is one of the strongest bases, right? We were given a list of all the strong acids and strong bases, and NaOH was definitely on that list. But also the other thing is it would be a very, very, very poor nucleophile. It does not follow the rules that I talked about in the other video, where nucleophiles must be weak bases, right? And we just said in the point above this that NaOH is a very strong base. So this would not result in a nucleophilic attack. It would result in an acid-base reaction. So on this and on those two carbons, I have 3 hydrogens on each of them, and they're all equivalently acidic. So this base is actually going to capture this hydrogen, and this will give its electrons to the carbon, and then these double bond electrons will go onto this oxygen. So you would have something like this. And this is what we call the enol version of the molecule. And just a second to talk about the tautomerism part of this. All this means that you're going to have some sort of equilibrium between those two states, right? That means that in solution, you're probably not going to, especially if you have a solution which has base in it, right? You're not going to just have the ketone. You're also going to have the enol version of this molecule. And tautomerism just means that this is kind of a rapid equilibrium that happens between the two of them. Okay, so now we can talk about some applications of this tautomerism. Let's talk about something called the Aldol reaction. So this says that a ketone plus a ketone, or an aldehyde plus an aldehyde, or a ketone plus an aldehyde. So any combination, basically what I'm trying to say is any combination of ketones and aldehydes can result in something known as the Aldol reaction. And the reason that I stated that Keto-Enol tautomerism relates to this is because we're actually not going to be using the ketone version as this nucleophile. We're going to be using the enol version. And before I get into that, let me just zoom in here and explain something about this enol. In this molecule, the reactive nucleophilic part of this molecule is not this charged oxygen. It's going to be this double bond right here, because as I said before, oxygen is a strong, oxygen is a good electronegative atom, so it likes to hold on to the negative charge, versus this carbon right here, which is not electronegative, much less electronegative than the oxygen, and there's an electron density right here because of those two double bonds, so that makes it reactive. That makes it have a lot of electrons near it, which makes it nucleophilic, right? So let's go ahead over here and start. What does this tell me? These aldol reactions usually proceed when they give you a ketone, or like I said, ketone or aldehyde. I'll just do it like this. And then they give you a base in water, And then down the line, they'll give you some sort of acid. And they will expect you to give them the products, right? So let's go ahead and I will just randomly choose an aldehyde, right? I could have used a ketone. I could have used this right here, but I'll just choose an aldehyde. It would give you, the mechanism will still be the same, and the way of thinking about this will still be the same. So I have a base, and I will just go ahead and say NaOH again, right? So then this base has these 3 hydrogens to pick from. Notice how there is a hydrogen over here, but this is not acidic, right? And that's very important for you guys to make that distinction when you guys are having questions or something about this. This hydrogen, make sure to never take away this hydrogen when you're doing acid-base reactions like this, right? This is not acidic. These carbons on the these hydrogens on the carbon adjacent to the carbonyl are the acidic ones. So this will capture this hydrogen or any one of these, and it will donate a double bond, and this double bond will go onto the oxygen. So you'll end up something like this, right? So that's your step 1. So you might be thinking, well, that's done, right? That's the entire reaction. But actually, no. What you're going to do is you're going to add this to the original aldehyde. So, and the reason we do this is because this is not something we have to force. This is just something that exists in the reaction. Like I stated earlier, if you have some sort of beaker and you have this aldehyde or this ketone, right, and you add a base to it, you're going to have both of those forms. You're going to have the enol form, this is what that is, that's the enol, and you're going to have, this is not a ketone, but I'm going to go ahead and say this is the keto form, right? This is a tautomerism that exists in between them. And as I stated earlier, this is reactive. This right here, this double bond right here is a reactive double bond. So just the fact that you added the base, you're going to have this reaction go to completion. So you can't just get the enol and stop there, because the enol on its own will react with the aldehyde or the ketone. So how does this work? Well, what you're going to see is that you're going to see that these electrons over here are going to reform the double bond, and these electrons are actually going to attack this partially positive carbon right here, because this is partially negative and this is partially positive. So these electrons are going to attack this partially positive carbon, the carbonyl carbon, and these electrons are going to go onto this oxygen, right? So you're going to end up with something like this. And I'm going to draw this right here. So let's go ahead and do it right here. So I'm going to draw this first. There's a double bond right there, and then there's a carbon right there. And so far I'm done, right? Then I will join this bond. I'm going to go join this bond with this carbon right here, and that's going to be demonstrated by this, right? And then I will have the carbon, I will have the OH group, and that's it. Actually, let me go ahead and erase this OH part because that doesn't come in just yet. Right now, so far I have an O minus because this comes in here, right? So just to demonstrate for you guys what everything is this, right? This is this, okay? This is the bond that I formed. This is the new bond that didn't exist before, right? And this carbon is this carbon, this oxygen is that oxygen. And this bond, like I said, is between this carbon right here and this carbon right there. Okay, so now that we have this, the second step was to add the acid. And adding this acid, all it's going to do is it's going to, let me erase this instead of writing it again. It will just give this an OH. It will just, protonate that. And this is called a hydroxy beta hydroxyaldehyde. So let's go ahead and do a couple more examples, and that way that can explain it a little bit more, and hopefully you guys can get the idea of what is going on. Let's try something a little bit more complicated. Let's try something like this. Right, so this is obviously a ketone. So let me go ahead and use a highlighter to show you that this is a ketone. This is a carbon group, and this is a big R group right here. But we're just going to look at that part. And I'm going to add another ketone, which is also pretty complicated. Right? And I'm going to add those two things together. So here's something that you guys need to understand for this kind of reaction is you don't always have to have the same starting molecule reacting with itself necessarily. You can have one or more reactants, different ketones, different aldehydes, a mixture of ketones and aldehydes, right? You can have different things and your reaction will still work. So let's go ahead and show you guys what this would do, what this reaction would do. So obviously I'm going to need a base, and again, right now, here is something that you guys, that's really important when it comes to this. So let's go ahead and zoom out. So over here, I only had one option. I only had one carbon right here that was acidic, right? I mean, that had acidic hydrogens on it. That's the only carbon that had acidic hydrogens on it. Let's go over here and count how many acidic hydrogens I have. So I have 3 from this carbon, 1, 2, and 3 hydrogens. But I also have 1 hydrogen right there, right? And now the question becomes, which hydrogen is the most acidic, and which one will the base pull off when the base attacks, right? So this actually brings up a really important concept, which is something that's known as a thermodynamic versus kinetic product. Right? So products. With the thermodynamic product, you're going to have to need heat to force this thing to go forward. And it's thermodynamic because it's stable. So you need heat, but it forms stable, the most stable product. Kinetic product is the least stable one, and it usually is at cold. Sometimes it's at negative, degrees Celsius. That looks like an E. Let's fix that. And also, it's the unstable one. To get the thermodynamic product, you're going to need a small base, and I will show you why in a second. For this one, you need to have a bulky base. Okay, so let's go ahead and put it all together. So for this one, in order to pull off one of these 3 hydrogens that I have over here, do you guys think I would need a thermodynamic reaction to occur, or would I need a kinetic reaction to occur? Meaning, do I need to add heat, and also do I need to pick a small base, or do I need to pick a large base? So those are decisions that scientists have to make. And seeing as this carbon right here is not substituted, there's nothing around it, it's it's pretty much a methyl group, right? This right here is pretty much a methyl group sticking out, and it's not substituted, right? So that tells me that it's very accessible, and I don't need a small base to squeeze in to fit it. And also, if you think about what would happen if I were to take a base right now and capture this hydrogen, and I would have a double bond here, and this oxygen would go over there, I would have a double bond right there. And versus, let's go ahead and think about this. If I were to pull off this hydrogen, what would happen? Well, if I were to pull off this hydrogen, my double bond would go here, and I'd have that again. So I would have something like this. Right? Or, so that's what that would look like, right? So now let me go ahead and compare. Which one is the most stable? Well, it looks like this is the most stable. We also said that this doesn't need this one. This is the most stable product. So if I know that it's the most stable product, that means this is going to be the thermodynamic product. That means in order to get this, in order to pull off this hydrogen right here, I'm going to need a small base. Small base would be something like an OH minus, right? In order to get this, however, I don't need a small base because this is pretty accessible. It's actually really accessible, right? So I would need something like a bulky base, something like LDA, for example, right? And let me go ahead and erase this word unstable here. I'm going to say less stable, because it is pretty stable, but it's much less stable than the thermodynamic product. So, and I also know, because of the decision that I just made, I also know the temperatures that each reaction is going to go at. So let's go ahead and put everything that we just talked about together and start. And I'm going to change these two benzene groups for X's. So just X, right? Okay, so if I were to add NaOH and heat, this is what would happen. I would have a small base that would take this hydrogen, capture it, right? An OH right here would take away this hydrogen, and this hydrogen would donate its electrons to this carbon, and these electrons would go there. Go ahead and do it in a different color so it's a little bit easier for you guys to see. So then I would have this O minus plus my other group that I haven't done anything to. Also, something to keep in mind, why didn't I do any base reductions to this? Well, because there are no hydrogens that are acidic on this benzene group or on this benzene group right here. And the only two carbons that would have had acidic hydrogens are these ones. But unfortunately, these ones, there are no hydrogens here. There's not a single hydrogen here. So therefore, I couldn't have possibly added a base. And adding a base to this wouldn't have done anything. Okay, so now that we have this, we can start our reaction and explain how it will go. Like I said earlier, this is the reactive part. So I would have these electrons from the oxygen go back down, and these electrons now would attack in a nucleophilic manner, and those electrons would go over there. So I'm going to draw this part first. I'm going to draw the X's right here. O minus, and then another X. And I'm going to draw this bond between this carbon and this carbon, right? So let's go ahead and draw that. So on this carbon, I have two groups popping off. And then I have the bond. And then I have another carbon and a double bonded O. So I'm sorry, I confused myself a little bit because I just forgot to draw this group right here. But this is this. This is this, right? This is this. And this entire group coming off of that carbon is this entire group coming off of that carbon. And lastly, this entire group is this entire group. So you can do it like this, or you can do it like that. It doesn't matter which molecule you start from. They both will give you the same product. So this is my thermodynamic product. They both are the same. This is my thermodynamic product. Okay, let's do the kinetic product, and then we can wrap up this video. So let's go ahead and start again, and this time I will not forget the structure of the molecule. Plus I will do a pH here, and then another pH right there. Okay, so now that I want to know that I want to do like kinetic product, I know I'm going to have a big base, LDA, and it's going to have to be something really, really cold, like negative 78 degrees Celsius. So let's go ahead and see that these are the 3 hydrogens that are accessible to this. So this is too big to squeeze in here. So it would have to capture one of these hydrogens. And that's the product of what it would give. This is the product. So you have an O-, you have a double bond right there, and pH here, and a pH right there. So then this, again, is going to attack this carbon and that. Okay, there we go. It's always good to double check. That's what I always do. It's just sometimes you draw an extra carbon or you miss a carbon or something. So just always double check. So this is this. This is this. This group is this group right here. This is this. So we have the exact same molecule, and this is the kinetic product. So as you guys can see, it does take a lot. It takes a lot of practice to get these down, but this reaction is really fun, and it kind of allows you to think a little bit about, well, which reaction is it going to go through? And by the way, just a clear tip, if on the test or on your homework or whatever, you see that the professor gave you a negative 80 degrees Celsius and a large base, he's kind of trying, or he or she is trying to clue you in on the fact that you need to have the kinetic product. If they give you something small like an OH maybe, and I don't know, 80 degrees, or I think 80 is kind of too much. Let's do something like maybe 30 degrees, right? Then you might know that, oh, this is thermodynamic product. So it's all really fun, and just to recap, keto enol tautomerism is just this equilibrium that exists between the keto and the enol form, and this happens because a base attacks a hydrogen that eventually gives rise to this double bond, the enol. And then from that we can go ahead and do a couple really cool reactions called Aldol reactions. And then I showed you an example of a very simple one and then a kind of a tougher one that would make you have to think about thermodynamic versus kinetic. So thank you guys for watching. Please like and subscribe. And